A figure has symmetry if it can be mapped onto itself. Okay? If you can flip it and it's itself, or if you can rotate it and it's itself, then it has symmetry. It's considered symmetrical. It has line symmetry if it can be flipped onto itself. It has line symmetry if it can be flipped onto itself. And rotational symmetry if it can be rotated onto itself. And then add this. In 180 degrees or less. Line of symmetry. That's the line. The figure is the line. The figure is flipped over. To map itself. Got it? Getting it? A figure. Oh, golly. With rotational symmetry, also has point symmetry. Questions?
What's point symmetry?
Point symmetry is if look at 587 on the top. I'm going to try to draw the best hexagon I can. That's not very good. That's 16, that's got to be 16. Square, right? It's got rotational symmetry, agreed? Because if you take this shape, you rotate it 90 to the left, it's going to be itself, won't it? Okay. Because the points are going to match up. Okay.
The points will be in the same place.
Yeah, I mean, that point is going to be right there at 90 degrees. It's going to be on top of another vertex of the shape. That makes sense? Yeah. All right. So this has rotational symmetry. It's going to be itself at 180 degrees or less, isn't it? Okay. It'll be itself in how many degrees? It'll be itself at 90 degrees, won't it? Does it have line symmetry? Yeah. It's got line symmetry there. Where else? There. Both diagonals, doesn't it? Okay. 3. How many lines is that? 4 lines of symmetry, doesn't it? Okay. If you flip that shape over any of those lines, it would map itself, wouldn't it? But if you took a rectangle, does it have that many lines of symmetry?
No, only just 2.
Yeah, it's only got a vertical and a horizontal, doesn't it? It's got one about there and one about there. Does it have rotational symmetry? Rotational symmetry occurs if it's itself in 180 or less. So if you rotate that thing 180, it's going to be itself, isn't it? Okay, but nothing less. Does it have these diagonal lines of symmetry? If this is A, and you reflect it over this line, over that line, won't A be up here? It won't be sitting on it. It won't be itself, will it? So it doesn't have that. That's not a line of symmetry, but that is, and that is. Clearer? Look at page 588. Triangle. Does it have rotational symmetry?
No.
Got a no and a yes.
No.
Josh, why no?
Because the only way it can be itself by rotational symmetry is if you turn it 360.
If you rotate this thing, I mean, if you pick a point here in the middle, if you rotate it 180 about that point, won't the bottom be up here on the top? It won't be itself, will it? If you rotate it around right here, the bottom will be up here, won't it? And it doesn't have rotational symmetry. Does it have line symmetry?
Yes.
Yeah. Well, can you put a line through right down the middle? Does that cut it in half? If you took that triangle and flipped it over that line, would it be itself? It would map onto itself, so it does have line symmetry. It doesn't have rotational symmetry. Look at the star in 2B. Does it have rotational?
Yes.
Yes. What about line?
Yes. 5.
How many degrees of rotational symmetry?
72.
How'd you come up with that so fast? It says 72 in the book, but if it didn't say 72 in the book, you would divide 360 by 5, wouldn't you?
Oh, I didn't see the 72.
So every 72 degrees of rotation, that star becomes itself again. So it has rotational symmetry. Reflectional symmetry down on the bottom of 588. Yes.
So you can divide 3 by 360, and if it's more than 180, you know it's not rotational.
No, not really, because 360 divided by 3 would be 120. You got to almost look at the shape. If you had an equilateral triangle, I don't know if I can draw one or not, but let's assume that's an equilateral triangle, that all the sides are the same. Well, if you rotate this thing, now if you rotate it 120, will it be itself? This one will be, won't it? Because it's equilateral. This one won't be, though. Okay? When you rotate this vertex 120 counterclockwise or clockwise, that shape's gonna sit right back on top of itself. So this one has rotational symmetry. If you rotate this thing, you got to rotate this thing 360 to make it look like itself again, don't you? Okay.
So the only time you'll be wanting to divide vertices by 360 is rotational symmetry.
Exactly. Yeah. They'll say if it has rotational, does it have rotational symmetry? Yes. And then how many degrees? Or at how many degrees? Then you would divide. But if it doesn't have rotational symmetry, then there can't be an amount of degrees that it.
Mr. Olsenback, you always divide by 360.
Yeah, because any shape that has symmetry or anything that's rotated all the way around is how many degrees? Okay, because a circle consists of 360 degrees. 3D, three-dimensional. Three-dimensional symmetry. Two kinds. Reflectional and rotational. Alright? So 3D symmetry, reflectional. If the object can be cut in half. Two congruent halves. Look at that bowl on the top of page 589. The bowl on the left. Does it have reflectional symmetry? Can you cut that bowl in two congruent halves? Where would the saw blade go? Right? Vertical down the middle, wouldn't it? And that would cut it in two congruent halves. So it has reflectional symmetry. If you cut it in half horizontally, it wouldn't, would it? But you can cut it vertically. And then you've got rotational symmetry in 3 dimensions. And that's if the object can be rotated around a line. If an object can be rotated around a line, and remain itself. So if you look at the bowl again, does the bowl have rotational symmetry? And where would that line of symmetry go? Vertically? Right through the middle though, wouldn't it? Doesn't have to go up and down through the middle? So if you rotate it around that line, it stays itself? If you cut it in if you put a line right through it left to right, is it itself? It's not itself anymore, is it, when you're rotating it that way? Okay? If it has rotational symmetry, you have to be able to rotate it around a line and it just stays the same. And it's probably not, well, probably like a perfect cube. A cube would have rotational both directions. Or a sphere, a basketball. You can go that way and rotate it left to right. You can go that way, rotate it front to back, and it's going to stay the same. Yeah?
If it has rotational symmetry, won't make it on other ways.
It still has rotational symmetry, but you have to be able to describe where the line of symmetry would be. A vertical line through the center, a horizontal line through the center. This pen holder, does it have reflectional symmetry? Can you cut it in half? Can you cut it into two equal halves? You can't, can you? Because that helmet's kind of offset from the stuff on the ground. Right? If you cut it in half this way, then this half's going to have a helmet and that half won't. Right? If you cut it right through the helmet, then this half's going to have the football and this half won't. Okay? What about rotational symmetry? If you put a line right down the middle of it and you started to rotate it right now, is it itself?
No.
It's not. So it doesn't have rotational. Okay?
It has no symmetry.
This doesn't have any. Right? Yeah, if you rotate it at 180, it's not itself. Alright, any questions?
What time do you eat out of this class?
It's on the board. Page 589. Page 589, 1 through 19. We got to get back in the habit of checking headline every night.
Was there homework last night?
Yes, sir. The expectation is that you'll be working on the assignment in here until the bell rings or until you've finished it and you've checked all the odds in the back of the book and you don't have any questions. Kevin. Go. A couple minutes to get busy. Okay.